Hello everyone. In this tutorial, we will see how can we model a linear elastic beam. For example, on my screen, you see a simply supported beam uh, loaded with uniformly distributed load over the whole span. Say we'll use elastic steel material or any kind of elastic material. So there is no plasticity, there is no fracture or anything. This beam will continuously deflect and continuously the stress will evolve as long as you keep loading. So we are not applying any displacement load here. We are using uniformly distributed load, say 50 kip per linear feet of this beam, and the beam is 10 feet long. The cross section is 12 inch by 20 inch. So if you load this beam with this support condition by 50 kip per feet uniformly distributed load, what will be the stress condition along the whole beam and along the height or width of the beam? So we know from our mechanics of solid or strength of materials or theory of beams how the stresses evolve, right? The flexural stress, the shear stress, and then the combined stress, say, maximum principal, minimum principal stresses, shear stresses. We can see all kinds of stresses from Abaqus analysis. So I hope it will be a great learning, great lesson for all the engineers, and also who is learning Abaqus. It will be really helpful too. So after this beam, I will model a beam with linear, like elastic plastic material that's actually steel. So steel is not elastic, right? So after yielding, it shows some hardening, and beyond that reason, we call it a plastic material, and sometimes we just simplify it with bilinear elastic plastic material. So I will show that result as well, because that's important to understand the structural steel behavior, like the steel building, how a beam will fail. So um, uh, I will just for simplicity model this beam as a linear elastic beam. Then we will use linear elastic plastic beam. I'll continue lecturing about how to model concrete beam with reinforcement, with fiber reinforced polymer, etc. So that's my target. Let's start with elastic, linear elastic material now. So again, my total beam is 10 feet long, but the supported length, that means the span between two supports, is 9.5 feet. So I have 3-inch overhang on each side. So let's go to Abaqus. I opened it. The first thing in Abaqus I want to do is uh, change the current work directory. So if you open fresh Abaqus file, like a new Abaqus, if you just click or select Abaqus CAE, it will ask, it will just select the work directory as temporary file in the C drive, and all the analysis data will be saved in that directory. But I don't want uh, I don't want my data to be saved there, so I change the directory first. To do that, I just go to File and go to Set Work Directory, and you can select your folder from here. So if you just select this option, you can choose your um, file directory, and it will save all the files in this directory, okay? And also I go and save it or save as the file where I want to save it. So say linear elastic beam uniformly distributed load. So it will be saved here. Again, this is the location where I'm saving this file, but once Abaqus perform analysis, it will create a lot of file. You'll submit the job and you'll see a lot of files will be created. It will save all those files in the current directory. So that's why if I want to save my those files in this folder, I select that as the work directory. Okay. So let's save it as this file. And as you know, Abaqus has this model tree here, and you can go to, you can like start each module or branches in the model either from this model tree or from this module option. So we create a part first. So I'll just create one part because my beam is a linear elastic beam. And in one of my previous lectures, I said for the simple beam, to avoid too much computation and too much convergence issue, we use just an area of the beam as support. So I'll not create a steel plate or a cylinder or a half cylindrical body to represent the support. Rather, we'll select a surface area of the beam as the reaction support reaction area. Okay, so let's create a part and name it as beam, or just part. It should be 3D and it's deformable, and we'll use the solid shape function and definitely extrusion. Extrusion mean how are you going to create it? So once we create the cross section, we'll ask it for longitudinal extrusion. Or if we create the side face, we'll ask for the through the thickness or width directional extrusion. Approximate size doesn't matter. I'll just click on OK. And now let's select the um, beam face, because I don't want to select the cross section, although I can do, but that will make things complicated. So I want my x-axis, as you can see here, I want my x-axis to be my axis 1, y-axis to be axis 2. So y is vertical and z is out of plane. Okay. And I want my beam to be on xy plane, so that the load will be in vertical y direction and length will be in x direction. So what I will do is I'll just create the side face of my beam. Okay, front side or back side. And definitely we can create a rectangle here, and then we can go to edit or add dimension option, and we can say this side, my depth of my beam is 20 inch, right? So I'll select 20 on this side, and the length of my beam is 10 feet, that means 120 inch. So my unit will be, say, pound inch. Okay, and you should know that Abaqus is unit free. That means you need to have consistent unit, and your results will be in that unit too. So for example, if the length unit is inch and your force unit is pound, then your stress will be in psi. If your length unit is in millimeter and force is in Newton, say, then your stress will be in Newton per square millimeter or megapascal. So you need to assume which unit you are using, and the stress, strain, everything will be in corresponding unit. Okay, so I'm modeling in FPS unit or US customer unit. So that's my side face of the beam, 20 inch deep, 120 feet, 20 inch wide. And when I have the correct dimensions, I click on this cross section and click on done. And now it's asking the width of the beam. So what should be the width of this beam? Okay, so I know that's 12 inch for me, so I'll select 12 and click on OK. Now you can see it has created a 12 inch by 20 inch, 12 inch wide, 20 inch deep, and 10 feet long beam. So we can see the dimensions also. I'm not worried about this dimension now. Once we create this part, I will just go to the next module, click here, or you go to the materials section. So I go to property section, and it shows create material or material manager. If you click on this one, it will show this part, or we can create here and then create again. So if you have a material, let's name it as steel material, for example, and then we go to general and we insert the density value. So it's in PSI, as that FPS unit. That means our density should be in pound per cubic feet, and we know for steel it's 490 pound per cubic feet. Okay, once we click on that, it should be saved automatically. Like, we need to definitely click on OK later, but let's insert the mechanical property. As I said, the material behavior is linear elastic. So we go to the mechanical option, mechanical property, and then elastic. It's asking for Young's modulus, the modulus of elasticity of the material, and it's also Poisson ratio. So we know the Young's modulus for steel is 29 million psi, right? So our E is 29 million psi. That's how much? 1, 2, 3. Let's use comma to make it easier. So that's 29 million psi. And definitely, if I draw the linear elastic material is basically, say, if that's my x-axis, and then I need another shape. So that's my, sorry, that's what the vertical is y-axis and horizontal is x-axis. And if it's linear elastic material, the material properties is like this, right? So that's my strain in x-axis and that's my stress in y-axis. So say if this is my stress sigma, sorry, stress sigma, and that's my strain epsilon E. So the slope of this line will be the elastic modulus. So it will keep going as long as the strain increases, the stress will increase linearly. So that's how we define the linear elastic material, okay? And as you have seen, we are using elastic steel material here. So we go and just insert the Young's modulus and also the Poisson ratio. So it's 2, 9, how many zeros? 2, 9, 8, 2, 9, and then 6 zeros, okay? 1, 2, 3, 4, 5, 6. And then we know the still Poisson ratio is 0.3. So we click on this, and for plastic material, if we want the elastic plastic steel, then we need to go to plasticity and click on plastic. It's asking for yield strain and strain. Yield stress and plastic strain, we need to insert at least 2 rows. I'll show it in a later video, but we are not using this now, so I'll just delete it, okay? So I have density and only the elastic material properties here. You can see whatever I have defined for this steel material, it's listed in this material behavior box. So I'll click on OK. Is it asking something? Character long maybe. I think we have a space here or something, maybe. Come on. I don't know what's the problem. Let's see. Yeah, I think there was a character there. So in the name. So now we have defined the steel material and just dismiss it. It has saved it automatically. Now we go to once we have a part there, but we have not defined any property to this part, right? So to define that part, we need to create a section first. So we go to create section or go to the section manager. We create from there. So we create a section, say beam section, whatever name you want to give it, and definitely solid homogeneous. And then we use this material. So if we have defined steel, concrete, different materials, it will show the list and you need to select the appropriate material for this one. We have only defined steel, that's why only steel is shown here. So once we select this one, and that means we have a section defined, you can see it has created this one. If we need to change anything, we can come here and change the material, okay? Then as we have defined a section, we need to assign this section to our part. So we either click on this one, assign section, or section assignment manager. So it will ask the create option again. It's asking select the regions to be assigned a section. And we don't want, we can create a set, or we don't need it, but let's do it. And it's asking which section you want to assign. Say if you have a concrete beam, a steel plate, or a steel rebar, you have defined 3 sections there. So it's asking which section you want to assign to this part. So we have only one section, which is beam, and we want to assign it. Let's click on OK. As you can see, it has the color of the part has been changed. That means This color means that a section has been assigned to this part, and that section has material definition too, like which material this part is having, okay? For layered composite, we go to the other option. We don't need it right now. Here we can partition the bottom face of the part. We can do that in part option too. So what I want to do is, for my support, I want to create an area, support area, say 2 inch or 4 inch wide. So what to do that, I just partition the face of the uh, beam, and to do that we use this option, but we need some reference plane. So I use the parallel plane, and you can see that's the rotate view option. So if you click on this one, you can rotate your beam as you wish. And to get out of this command, you just click on the cross button here and it will take you to the previous command. So now it's asking select a plane from which to offset. So let's select the right face and then enter value, and you can see the arrow here, right? And I want a plane inside my beam. So let's flip that direction, click on flip here and then okay. Now it's asking the offset from this plane for the next plane. So I want my um, I want my support center from 3 inch from the end, right? So let's say 1 inch from the part, and then I'll select a 2 inch wide support. So I need another plane, and that will be 3 inch. Sorry, am I making mistake? If I want, I think I made a mistake. That had to be 2 inch, so I can have 2 inch wide plane, wide support. Then it will be. So let's create another one. We'll delete this one. Okay, enter value. Okay, let's create two first. Then I need another plane from this one at 4 inch. Okay, then it's at 4 inch. I need to create that on the opposite side too. Cross, select this button, enter. Okay, 2 inch, and then another at 4 inch. Okay, now we cross this option and come to here, partition face. We use datum plane. So use this one, partition face, use datum plane. So it's asking select the faces to partition, and we definitely go to the bottom surface. We select this surface and then click OK. Select the datum. Let's use this one, create partition, select this surface, this one, sorry, this surface, okay, this face, okay. And now also this surface, yes, first one, yes, then the remaining one and the other surface. So if we have an extra datum plane, that's okay, it's not doing anything. Or if we want to delete it, we can come here, delete feature, and then click this option, done, it will click, okay. It will delete that part. So for the 3D view, we click on apply isometric view, this option. To see XY view, the front face, we click on XY face. We have 7 view option here, and we also have rotate view option too. So now what we will do, I think I need to partition this face a bit more. Sorry, I'm taking long, but I think it will help you learn step by step. Sometimes we make mistake, and how can we come back from there? So we need to learn a lot. I'll also create partition between two faces because I want to assign a reference point in the middle of this beam, although sometimes we can do at the end of the beam, but I prefer to have a reference point in the middle of the support area. So that's why I am partitioning this face again, but we are using the shortest distance between 2 points. So now you can see it's showing the endpoints of lines and the midpoints of the lines too. So now you can see I have created some partition there. Okay, it's done. Now let's go to assembly. So assembly is, for example, if you have created a beam, concrete beam, and then is reinforcement, and you need to create one part for longitudinal reinforcement, one part for shear reinforcement. Then you might have 10 shear reinforcement in your beam, three longitudinal bar in your beam. So you need to copy those parts into the beam in the assembly area so that you can have your full beam together. For me, I have only one part, and that's my assembly. I'm not even creating a external or extra support. So I will have only one part in my assembly, but still I need to create an instance of my part in the assembly area. So I create assembly parts from instances from parts. Yes, definitely. And as you can see, I have only one part. And we if we have multiple parts, we can use the auto offset option. So they will not be copied at the same origin. As you can see, my origin is probably at this corner of the beam. So if we do not offset them, everything will be brought here, referring to this origin. So your reinforcement will be inside this beam and you will not be able to see it unless you use other option like create display group here. But if you click on the auto offset option, you'll see they will be separated. Okay, then you can move instances from here. So we'll see it in a later lecture. Now I have a instance here. We have more options to do. Say if we want to move a part on, we can translate. We want to create a pattern, linear pattern, radial pattern. We have different editing option too. If we want to rotate it, if we want to translate to with reference to something, we can also, you see, we can partition face, partition section, lot of things here. So I will just leave it like this in the assembly module. We now need to go to the step area, and it is step module, and we can just click on create a step or go to step manager. It has the create option here, and say this is the loading step. Okay, so we assign the boundary condition to this beam in the initial step, and then the load we apply is going to be applied in another step, a step later. Okay, that's why you can see it has already the initial step, but to apply the load we need another step, which is say the loading step. We need to create that, and it's a general. And for linear elastic analysis, we use static general. For some beams, we use the dynamic explicit. For example, if we want to see the brittle failure of concrete beam, a dynamic explicit dynamic analysis will give us better um, presentation of the failure modes. But for this linear elastic analysis, we just use the general static. Okay, and it's once we click on this one, it's asking the basic time period. So the time period is one here. That means Abaqus will take uh, the total time to complete the job, to complete the analysis as one unit, and you can divide this 1 unit of time into millions of time increments. Okay, so we do not change it. We leave it like this, but we come to the incrementation option. We increase the maximum number of increments to say 1 million or 1 billion. Increment size, initial increment size, let's give it a small value. We also decrease the minimum increment size to say -10, uh, 10 to the power -10. So as I said, when it's a Abaqus solves your problem with some numerical procedure, right? Newton-Raphson method or some method. And to do that, it fragments the whole job into very small parts, and then it iterates the procedure until it reaches the final solution. So that's why it needs the increment size. Let's say the maximum increment size is 1, minimum is 10 to the power -1, 10. And initially, let's assume, say it will use the increment size as 0.001. We don't need to change anything here. We click on OK. Oh, so we could change the nonlinear geometry option. So we definitely want it. So we had to change this one. Let's keep the nonlinear geometry part on, so that when your beam deform, if the geometry changes, definitely it will deform and it will change its nodal position, right? So we want that nonlinear geometry to be included in the analysis. So once you create this one, you come here, field output manager, or create field output option. So it has this, it has created a field output option. We can just come here and edit, or we can create a new one. We do not want to see all these options. So it will create a very big output database file if you keep all this selected, okay? So I will just select the stresses and strain. From a strain, I'll just select total strain. I'll not select the plastic strain components, Pmax, logarithmic strain, etc. I do not want all the displacement components, but I want the translations and rotations. So that's fine. And I want the reaction forces. So I do not need the concentration force too. So as I said, if you select multiple option, it will create bigger file and it will take longer time to do the analysis. We also come to the frequency option, like how often do you want your analysis data to be recorded? For example, I want from the whole model domain, you can set different domain too. We have created a set already, right? When we selected the beam section, it created a set. So I don't need that, but I want my data, fill out data from whole model. So it will select at each element level and at each node level too. It will save the data and the data I requested. So stress, strain, translation, and reaction force. But I want my data at X unit of time. So let's say 0.01. That means that the total time is 1 and we are requesting data at 0.01 second. That means 1 divided by total time, 1 divided by 0.01 is 100. So we will have 100 data points. If you want, say, 1000 data points, more data points, you can select 0.001. If you want even more data, 0.002. Definitely, it will take more time and um, you will have more detailed data. So it depends on how you want to see your data, okay? And we definitely want output at exact time. So it will give us the data at 0.0001 second, 0.02 second, 0.03 second. So we use this option, output at exact times. And definitely it should be at integration points, and we click on OK. So we change this one. If you want some, for example, the reaction forces, you request some history output data, but we'll have the field out request support reaction from field output data. I will show it. Um, we do not need to create any history output data. Still, let's create some. Sometimes it gives error, like it gives us message that you have not created any history output data. So let's do the same thing, like the field output data, and we want to see only the reaction force. Sorry, whole model set. I think we don't need to select anything, but it will not go. So let's select just stresses, okay? And we can select further stresses, the like what kind of stress we want to see. Maybe we just want to see this two stress components. I believe that will be fine. So we have created a history output too. Now let's go to introduction. So I want to couple my support area to a single point. And I want to create, for that I want to create two reference points, one at the center of the left support area and another at the center of the right support area. So I have just created two reference points. You can see RP1 and RP2. Now I come to this option, create constraint or create constraint manager. Then we create, let's name it left support area, and we use coupling. So to couple an area to a point, we use coupling, okay? Now it's asking whether you want to set this as a, uh, so we want to select this, sorry, select the constant control point. So when you select the reference point 1, it becomes red, and I will say this is reference point 1. If we create a set here, it will help us um, like extract the support reaction easily. We know that left support reaction is reference point 1. And now it's asking which surface area you want to couple this to this point. So we'll click on surface and then click here. I'll create this surface as a left support area. Done. And we do not, we want to couple all 6 degrees of freedom to this point, okay? It's done. We create another one, create, say, right support, coupling, continue. Select the reference point 2. As you can see, when you select it, it becomes fully red. And I'll rename it to RP2 here. Done. Now it's asking whether I want node region or surface. I want surface area, and this is right surface area. So done. I don't need any other coupling here. I don't need any interaction property manager since we do not have any contact or anything. So in interaction module, we are done. Let's go to load module and create 2 boundary condition first. So come to the create boundary condition or boundary condition manager option, and you can create. So let's say left support again, left support, and we want in initial loading. Again, you remember I told you that boundary condition will be applied in a step, initial step. Okay, so you need to select initial step from here. And from mechanical, we can go to either this option or displacement velocity option, displacement rotation option. Let's go to symmetry, anti-symmetry, or Encaster, and click on this reference point, RP1. I think we need to let's do it again. RP1 is not RP left support. I'll just do it like this. And we apply, say, if it's a simply supported beam on left support, we apply a pin. That means it cannot go vertically up and down and horizontally. It cannot go horizontal direction too. So U1 and U2 should be 0. Okay, which one? Pin. It's here. U1, U2 equal to 0, and it cannot go out of plane direction too. So all U1, U2, U3 is 0, but it can rotate about that axis. So you can see in initial step, this support, left support, this boundary condition has been created and it has been propagated to the loading step. Okay, we create another one for right support. Right support, we use the same option, initial step, click on OK. Now it's asking for the regions. We select this reference point 2. We say RP right support, done. And we apply a pins a roller support here. Okay, that means it cannot, it can resist the vertical displacement, but it will allow U1 and U3. And it will resist the UR1, that means out of plane rotation, and UR3. That means in the Z directional rotation, UR3. So we should not choose this option, sorry. U2, U2, U3 equal to 0, and UR1, rotation about x-axis. I think we should use this section, sorry. So it will have a roller support. Again, the support, both boundary condition has been created in the initial step, and it is propagated all through the analysis until the end, right? Now we dismiss this part, we go to the load manager or create load. So we go to here and then create a new load, and it's asking like in which step you want to create that load. We definitely want it in the loading step and say UDL, uniformly distributed load, and we apply it as a pressure, okay? If you want a concentrated force, you can apply that. If you want a line load, gravity load, pressure, different area. So for the uniformly distributed loads over the whole area, we choose a pressure option. Now it's asking which area you want to select for the area, load area. So I select this top whole surface, and I'll just keep it, maybe we'll name it top surface like this. And it's asking like how you want to apply this pressure, with total load or uniform load. So we are using the uniform load option. And you remember our loading is 50 kip per feet, but it's asking in pressure unit. So that's not pressure, right? Keep 50 kip per linear feet. We need to convert it into uh, kip per square feet. So our beam is 12 square inch. And we need to definitely apply the force in pound per inch square, right? So 50 pound per feet. So I need to divide this by 12 so that it will be 50 kip per inch. And then along the width, which is 12 inch, I need to divide by 12 again. So it's basically 0.347, okay? 0.347. This is very critical. If you do not understand, your stress condition will not be met clearly. So here it's asking how you want to apply the load. I need to select a RAM, or I need to create a function, create an amplitude. So I create an amplitude, basically use the tabular option, and on an Excel file, I just do this. So I type say 0.01, 0.02, 0.03. So it's better to have like this until you reach 1, and you copy this again and paste it on that side. So you copy this all whole 2 columns, Control C and Control V, and paste it here. So you can see, sorry, oops, I pressed the wrong key. So now it has created time, frequency, and amplitude. So it's better to apply in this fashion. So we are applying this load sequentially and with uniform increment, okay? And also remember, in Abaqus solver will make a small time increment to solve the problem and complete the analysis. So we have applied the uniformly distributed load here too. And now we go to the mesh option. So we need to mesh on part. We click on part. If you are on assembly, it will not do that because we created the part mesh independent. So we need to mesh the part individually. We cannot do mesh on assembly, okay? Now there are several options to select here, since this is a linear beam without um, any imperfection or even material non-linearity. So we just click on this option, seed part. We say our mesh will be 1 inch. So let's click on this one. You have seen the seeds. It's basically seeding the edges, okay? And we click on done, and then we click on this option, mesh part. So you can see it has done that. We have already definitely these are important, assign mesh control options. So as I said, this is a simply rectangular beam. So element shape, we can choose the hexahedron, and definitely structured technique for generating the mesh is a good one. We will have more talk on this. we can also assign element type. So select this region. We can select 3D stress, cohesive, a different like shell type element, um, continuum shell, pore fluid, different types of element library, element family from which we can select our element type. For us, it's like 3D stress only, and we are running a standard linear um, analysis. So these options are good for us. We don't need to change anything. When we do dynamic analysis, some of the options will change it. We'll see it later. But for now, just click on seed edges and then mesh part. It should create the mesh. As you can see, it has created a symmetric and all cubic mesh. Okay, there is no uh, like non-regular mesh elements in my whole structure. Let's go to the job option. We don't need to do anything from the uh, optimization part. And once the job is complete, we'll come to the visualization section. So let's see if we have forgotten anything. If we have forgotten anything, Abaqus will not complete the job and it will give a message before it starts completing the job, okay? Before it starts running the job. So let's go to this option, create a new job. I'll say this is job 1 and I will type my model name, say linear elastic beam UDL. Okay, and continue. Now it's asking if you want to uh, change the memory use. Like it's going to use 90% of my computer memory. So if you want to reduce or increase it, definitely if you use all of the memory here, other works will take long time for your job to be completed. You can use multiple processor. You can increase the processor time. We don't need to do anything with the standard Abaqus analysis with precision. For dynamic analysis, we need to use the packager option. But for now, let's just use maybe 4. Okay. So once it's done, let's save it again and then click on submit. So as you can see, keep a note on this message box. So whatever you have done, it has just gave messages here. You can see the job input file has been submitted for analysis. Now you will see another message whether the input file has been uh, com completed successfully or not. Yes, here the job 1 analysis input file processor completed successfully. So input file processor completed successfully means we did not make any mistake in the modeling and assigning properties, meshing, things like that. For example, if you have forgotten meshing the part, um, it will give a message before running here that you have that this job has part that it has not been that has not any mesh yet. So do you want to continue without that? Things like that. And it's also a good message that uh, it has completed the input file processor already. And now you can monitor the analysis, like how the analysis is evolving. You can see the total time frequency is, so it has completed 4% of the job. So a step time, you can see here, we can see it's propagate, is solving the problem very fast. So 19% of the job is complete. When it's 1, you'll see that the message will say it's completed. Okay. So for example, if you want to kill the job, that means you don't want to run the analysis anymore, you can come here and click on kill. It will ask whether it's okay to kill the job or not. I don't want to kill it now. And while it's running, sometimes some of the jobs takes 2, 3, 4, 5 days. Even for me, um, it takes 2-3 days to complete a job. So after it completes the 50% of the job, I can go to results and it will show that part of the result, whatever it has completed so far. So you can either monitor the job, or you can see intermediate results too. If you want to stop the job and do not continue anymore, you can kill the job as well. So I'll just pause it a bit here. I'll wait for the job to be completed. I think it will take maybe 1 more minute, but I'll pause the record and I'll come back once it's done. Okay, in the monitor job option, you can see it has reached a uh, step time or total time to 1, as we have inserted total time to be 1 in the step option. You remember? So when it's 1, that means the job is complete. And also you can see the message here, completed. It's showing date and the clock time too. Okay. If you need to see the messages, you can come here, status of the job. It will show at the end. You see the job is analysis has completed successfully. If the job is aborted, that means there is problem and it cannot converse the solution. You will see it will give you message here like the job has been aborted. Now it shows the job, this job has been completed successfully. So from the same file, you can create multiple job and submit it again and again with changing. It will create more ODB file with the job name, and it will save the data in your work directory. Okay. So let's go to results now, and it's showing just the deformed option here. Plot undeformed shape here. But if you want to see the deformed shape and plot contours on deformed shape, click on this option and it's showing the deformed shape, and it's showing von Mises stress. Okay. So to see a different stress, we can come here, click on this option and say, I want to see the longitudinal stress in the beam. So we definitely want S11. So S11 is the first. S is the stress. S is for stress. Definitely you can see it has the translation, rotation, stress, reaction moment, reaction force, logarithmic strain, things like that. So S is for strain, stress, and S11 is longitudinal stress. What the first one after S is, it indicates the axis to which my plane is perpendicular. So X is 1, Y is 2, and Z is 3. That means my plane is perpendicular to X is 1, which is X-axis. That means vertical section. Okay. And the second number here, it indicates the stress direction. So the section is vertical, that means beam cross section, and the stress is in X direction. So that's definitely longitudinal stress. So the vertical stress will be S22. The out of plane stress will be S33. So what will be the vertical shear stress? Vertical shear stress will be on the vertical surface, but in X direction, right? So uh, it will be basically either S12 or S21. But Abaqus does not show S21, it shows S12. And we know S12 is equal to S21. So it shows the shear stresses as well. Okay. Now, let's see the vertical stresses, and you can see it has um, given us the results in PSI, right? Did I? Sorry, I think I made a mistake here. This I inserted the load in KSI. Sorry, kip per square inch. Yes, so that's why the stress is very low, I will say. Let me go to the load section again and check my load. So let's come here. Yes. So we remember we are modeling everything in FPS units. So the force should be in pound per square inch. but I did not convert the 50 kip load to 50,000 pound. Let me check again. 50 times 1,000 divided by 24 divided by 24. So it should be 86.8, but I plotted this in kip. So what's the problem if we keep this load and keep per square inch? The problem is with the material elastic properties. So either we need to change the load here or the modulus of elasticity in the material property option. Okay. So in the material section, we inserted 29 million as the elastic modulus. That's in PSI. But if we insert 29,000, that's in KSI, then we don't need to change here. So you cannot have this mismatch, unit mismatch in your analysis. So let me change this to 86.8 a pound per square inch so that we can have the correct analysis data. And let's go to this option here again and submit this result, submit this job. So it's asking this job is already done and it has a file, and do you want to overwrite it? I will say yes, and it will submit the job again. Sorry guys, I'll wait for this analysis to be completed and I'll come back again. Okay, guys, I think I made another mistake actually on my calculator when I wanted to calculate the load in pound per square inch. So after the analysis, I saw the results and it was not matching with my calculation. So I went back and changed the load again. And you can see the load in pound per square inch is, so again, 50 kip per linear feet. That means I need to divide by 12 to make it 50 kip per linear inch, and my width of the beam is 12 inch. So in that direction, I need to divide by 12 again. So that becomes 0.347 kip per feet into 1000. So in pound per square inch, it's 347.22. I just inserted 347.2 pound per square inch. Okay, that's equivalent to 50 kip per linear feet of the beam on a 12-inch wide, 20-inch deep beam. So let's go to the results and see. We went to the job and it's completed, and we just see the results. And you can see here, that's stress S11. I will like to compare the stress at the top and bottom. You can see the stress is symmetric at top and bottom. Okay, the tensile stress is at the bottom, which is positive here, and the compressive stress is at the top and it's negative here. And also you can see at the mid-span, the stress is maximum. As you go towards the end, the bending moment is zero. So the S11 is mainly caused by the bending moment, right? So as you go from the mid-span to the end, the bending moment is zero at the support. So in this region, there is zero moment basically and zero flexural stress. So that's longitudinal stress, means it's flexural stress. The top in compression, bottom in tension for a simply supported beam under uniformly distributed load over the whole area, like this one. So the maximum moment is right here, and we know the moment diagram is like this, and maximum moment is here, and the stress distribution, if I draw on this beam, the compressive stress varies linearly on the top, and the tensile stress varies linearly too. And definitely, since this is a symmetric beam with symmetric material properties, the top stress will be equal to the bottom stress. So the tensile stress is equal to the compressive stress. You can see the tensile stress at the bottom is 8, almost 8.8 kip KSI. This is in PSI though. So, and at the top it's compression and it's negative 8 KSI. Okay. From my calculation, from the beam formula, we know the sigma at the bottom or top for iso uh, isotropic material like this beam with one material, it's my over I, right? So I is the moment of inertia. For this beam, it's 12 times 20 times 20 cube over 12. So that's basically I is equal to 8,000 cubic inch, sorry, inch power 4. And the moment we can calculate it from this maximum moment AM is equal to WL square over 8, right? So our support distance L is basically in the model. So it's 4 inch from this left end and 4 inch from the right end. So it's basically 9.33 feet, 9 feet, 4 inch. Okay. So in feet, it will be 9.33 feet. And M is WL square over 8. So if we do this, we get the moment to be, I'm calculating on my calculator. So the load is 50 kip per feet. The distance is 9.33 square divided by 8. So the moment is 544 kip feet. If I multiply this with 12, this will be, let's say, 544 kip feet, okay? And we need to make it kip inch so that we can insert it here. Let's do it here, right here. So M is 544 into 12, that will be in kip inch, and we have the moment of inertia in inch power 4, and y is half of this step, right? From here to here is y. So either compression or tension, y is same, and that's 10 inch. So if you calculate this, it's going to be exactly 8108, and that will be in psi. So that's the flexural stress we calculate from the flexure theory, right? For simple uh, what's called the isometric beam, or beam, linear elastic beam, basically. As long as there is no plasticity, this formula is valid. So we did not introduce any material nonlinearity, material plasticity in the model. So we should get that value as the flexural stress. And you can see from here, even if you extract the stress value from each node or element, you will see exactly 8 point. We calculated 8108. It's 8094. This difference is basically we have the load over this overhang 2 inch on both sides too, right? And there are some calculation inaccuracy. So anyway, we verified the flexural stress from this beam. Abaqus uses the finite element method. It does not use that simple beam theory. So it just discretizes the whole beam into this 1 inch cube pieces, and then at each node or at each node, which is the integration point, it calculates the stresses, strain, displacement, etc. Now let's get the displacement. So for this beam, the maximum deflection will be in the mid span, right? This beam will bend like this, say, under this load. By how much, we don't know. But the maximum displacement at mid span will be this much, and that can be calculated delta max as we know the formula for a uniformly distributed loaded beam, uniformly distributed loaded simply supported beam. The formula is 5 WL power 4 over 384 EI, right? So if we calculate the deflection at mid-span, so 5 is 5 formula, W is 50 pound per linear, sorry, 50 kip per linear feet, L is 9 feet 4 inch. So you need to insert that value in inches. Let me do it here, otherwise you can make mistake. So if we insert the load in pound per feet, then we need to insert the displacement here in inch too. So what should I do? 50 into, let's keep it in, no, let's divide it by 12 so that it becomes pound per inch, sorry, kip per inch. And then we can use the displacement in inch. So 9 feet 9 feet 4 inch is 112 inch, right? 9 times 12 plus 4. So that's 112 inch. So it should be multiplied by 112 power 4. Okay. Divided by 384. E is 29,000 KSI because the load is in keep. So I'll keep it in KSI, and I is 8,000 inch power 4. So the displacement we can calculate is as 5 times 50 divided by 12 into 112 power 4 divided by 384 divided by 2900 divided by 8,000. So that's basically 0.036 inch. So the displacement we got delta here is equal to delta max, basically the mid-span vertical deflection, 0.036 inch. So if we go to the view here, we can see the displacement, that's translation, and you can come here and see U2. So it will show the vertical displacement. Okay, it's not showing here. We'll just extract this value. So we'll come here, go to field output option, then select unique nodal, and then pick from view. So we need to select the variable as well. Sorry, unique nodal. We need to select unique nodal, then it will show the stress and displacement. Let's pick the displacement first. U2, we need the vertical displacement, that means U2, okay? And let's select a mid-span node. So I'll just select one of the mid-span portion here. We could create a reference point here too. So this is showing the displacement as we have plotted. We can save the data too. Let's save as it is. So I'll copy this data in Excel. Okay. Now come back to variable. We also want to extract the support reaction. So let's go to reaction force, and we want the vertical reaction, which is RF2. Y is 2, X is 1, Z is 3. So we need to unselect the displacement. I did it. Let's go to node set, and you see we created these sets. That's why it's here. So let's plot the reaction force at a reaction left support, which is reference 0.21. Save it. Okay, we can do the same thing for reference point 2. Plot it. It's the same because simply supported beam with uniformly distributed load over the whole span, the reaction force on left side and right side will be equal, right? But let's still save it, and we want to check this. Okay, so let's dismiss this data, go to this XY data manager. This is the temporary file which we have plotted, and we have the displacement here. So once it's blue, click on edit, and then click on Y here. You can see I selected the data at each 0.01 second. So it has created 100 data point for me. So I'm not worried about the time increment, rather I am worried about the displacement. Okay. So I'll click on Y. So it will highlight all the rows in this column. Select Control and C on your keyboard, and then paste it on Excel. So the left column is my displacement. I will put U2 in inch. I want to convert it into positive displacement. So let's say U2 in inch positive, but I'll just use the formula to change it into a positive displacement. The beam deflected vertically downwards, so that's why the displacement is negative. Okay, but let's extract the reaction force. You can cancel this one, come to here again, do the same thing, edit, click here, Control C, and come here, Control V. So this is left support reaction, which is in pound. Okay. Also copy the right support reaction. You don't need to close it. Come here and click on this one, edit, click C, Control C, and then paste it here. Control V. So that's right support reaction. The right support reaction definitely will be in upward direction. Left support will be in upward direction. That's why they are positive. So now we can have say the total force. So the total force we applied is 50 kip per feet. So 50 times 12, my beam is 10 feet length, right? So the total force is 500 kip. Let's add this air forces at the very end, and it should give us the total force, okay? So if I add this to, say, equal to this plus this both should give us 500 kip load. So that means 500,000 pound. As you can see, it's 4999.08 pound. That means it's 500 kip. So it applied that load in 100 increment. Okay. So that's the ultimate or final load. But how did it applied? It applied in 100 increments. Let's see when we applied just the first 1% of the load, 10% of the load. What was the load at that point? How much was the deflection, etc. We can compare it. So let's increase this uh, size, and we can see here this is the 50% load. Okay, but what I want to show is we can compare the load displacement response here. So we can say total force or top total force in pound or in kip. Let's do it in kip. Then we can have the force displacement response in kip inch. So I'll just add this and these two and divide by 1000. Okay. Oops. To make it in kip. So we can come to. Anyway, let's plot the force versus displacement response, although this is not very significant for this beam. But what I want to show here is the vertical axis is load and horizontal axis is load. Sorry, that's displacement in inch, right? As it's a linear beam, you can see the force increased linearly with displacement, and it should be. So for a linear beam, because we have a linear material properties, the force displacement response is linearly elastic. And later we will show the behavior of a elastic plastic beam. You will see a sudden change in the slope of this force displacement response when the non-linearity of material is hit. We'll see it in the next video. So I hope this helps you, and you can compare your mechanics of solid knowledge with the Abaqus analysis, and you can just see how the results look like. So this is the flexural stress. S12 will be the shear stress. The shear stress near the support is high, and also at the mid span it's high. We know that the shear for the distributed load, the shear is maximum at the support, and it continuously gradually reduces to zero at the mid span, and it goes in the other direction on the other support. So it makes sense. If we also want to see the principal stress, maximum principal stress, it shows the tensile stresses along the beam. It also shows the concentrated uh, uh, compressive stresses at the support, but as you can see in most part of the area, it shows the principal stresses. I believe if you see my uh, mechanics of solid classes, we have uh, a book open here. So these are the principal stress direction, okay? In the bottom part, it's horizontal because the shear stress is zero, but flexural stress is maximum. At the top, again, flexural stress is high, but shear stress is zero. But in the middle part of the beam, the shear stress is high, but flexural stress is zero. So the resultant force will be tensile in one direction and compression in one direction. So in the mid section, you have tension and compression at one element, but in two direction. So the maximum principal will show the tensile force and minimum principal will show the compressive force. And we can also see in this beam, you can see here, this shows for a concentrated loaded beam, although our beam is uniformly loaded, so this will not be perfectly matching, but you can see here maximum, the solid line shows the maximum principal stress, which is tension, and you can see its maximum at the bottom, and as we go towards the support, it reduces and it becomes zero. But the compressive stress, sorry, the minimum principal stress, which is compression, it's maximum at the top here, and it disperses as we go close to the support. So if we go back again here, you can see we are just seeing the maximum principal stress, which is maximum at the midspan, and as we go towards the support, it reduces continuously. If we go to the minimum principal, it shows the compressive stress distribution. So you can see the maximum principal stress is at the top fiber and at the midspan. As we go towards the support, it reduces continuously until it becomes like gradually close to zero. Okay, so the red part here is zero. You need to notice the stress magnitude here. If we want to move the beam linearly or in a direction, you can use this one. If you want to rotate the beam this way. I hope this helps. We'll see a second beam with linear elastic plastic material, and as I said, that will be very important to understand the behavior of a steel section. The steel section, which, as I said, steel is not perfectly elastic, so it's elastic plastic. So under the beam, if it fails, how is it going to fail? Until we cover that one, I hope you learn from this one. Thank you.